Okay, so the next thing that we have here, basically the next conic section that we have here is called the hyperbola. And basically a hyperbola is, you could say that it's two basically parabolas put from vertex, from the two vertex ends. Basically we had these parabolas in basically in this orientation, or we had them in this orientation, or we had them in this orientation, or in this orientation. So these were the four different orientations of parabolas. Now let's suppose that you have basically these two parabolas over here. Let's say that you have this parabola over here, and also this parabola over here, both in the plane. And of course you know that if I imagine that, or let me just draw one of them, that way it's easier to explain what I mean. So suppose that you have this parabola over here. So there is a focus over here called F, and there was something called the vertex of the parabola, which was basically this point over here. Now suppose that you have another parabola over here, and here is your vertex, here is your basically your focus. Now suppose that I somehow basically put the two basically xy planes together, and if I did so, I would get one single xy plane, and then the two parabolas put together this way. And of course it's possible, and this configuration over here that you can see, this is called a hyperbola. Now usually when we draw these hyperbolas in the xy plane, we usually draw them like this, meaning that we usually draw them, for example, something like this, and something like this, and then you have a focus over here, you would call this, for example, F1, you would call this F2, for example. And there is a vertex over here, and that's basically that. So this is called the center. This is a vertex. And this axis over here is called in the case of parabolas has been called the conjugate axis. This axis over here has been called the transverse axis. And that's all about hyperbolas. Now the way that we define a hyperbola is that if you pick any point on the hyperbola, let's say for example this point P x comma y, then the distance from this point to this focus, and there is some distance from this point to this focus, and this distance over here, meaning that the distance of the point, you get basically two foci. One of them is farther away from P than the other one. For example, in this case F1 is farther away from P than F2. So then the one which is farther away from the other one, the distance of that focus with that point would be PF1. and if you subtract from that the distance of the same point with the other focus, pf2, this is some constant. This is some constant value or quantity, and well, of course, as it turns out, it's actually equal to 2a, but it doesn't matter what it is. A is basically some distance over here. We will talk about that. But this value over here happens to be a constant, and it doesn't really matter, for example, which point, what sort of point you take here, as long as the point is on the hyperbola. For example, I can take this point over here, and then I have basically P1, for example, and this would be, for example, equal to P1F2 minus P1F1, and I can of course take, for example, this point over here. Then I would have, for example, let's call this P3. Then this would be equal to, for example, P3F2 minus P3F1, and so on and so forth. So that is actually the definition of a hyperbola, meaning that you can define it in the same way. It's actually been defined in the same way, meaning that as a definition, you can say that a hyperbola, as a definition, you can say that a hyperbola is the set of all points in the plane, is the set of all points in the plane, the difference of whose distances, the difference of whose distances from two fixed points, in the plane is a constant, or you can say is constant, or you can say is a constant. That doesn't really matter. And these two fixed points are actually these 2 points over here, which are the foci of your hyperbola. Now, that is basically all. Not all, of course. There is really a lot to say about a hyperbola, but that's basically the starting point of a hyperbola. Okay, so now what I'm going to do is basically draw a hyperbola over here, and then make a screenshot of that, because we are going to need a hyperbola all throughout the definition, and basically there are some other things related to the formula, to the Latus rectum, to other things. So we do need a hyperbola. I don't want to basically do it many times, so I'm going to do basically a hyperbola over here, something like this, and basically something like this. And suppose that this is the, well, there is some confusion, at least in my mind, related to these axes, but hopefully we will get to that basically in the basically somewhere it is these, for example, this axis has been defined as the x-axis, and this axis has been defined as the y-axis. In some other place, basically having the same orientation of the hyperbola, this axis has been defined as the conjugate axis, conjugate axis, and this axis has been defined as the transverse axis. Transverse axis. But we will hopefully get rid of the confusion along the way. And well, there is, let me draw 2 lines over here, so 1, 2, and 3, for example, 2 over here. Draw this line over here, so 1, 2, so that's 30 degrees, and then 1, 2. If I draw these lines over here, it's going to help. They're going to help me basically draw my hyperbola better. And it's actually interesting that a hyperbola, you can think of a hyperbola as some sort of basically in other functions. For example, there are some functions. For example, suppose that you have this function over here, and for example the tan function, if I'm not mistaken, now it's not necessarily correct, basically the shape of the function, but for example the tan function looks something like this, and then you have some line over here, and then the function at some point, the function tends towards that line. Not basically touching that line, but it goes just across that line all the way up to positive infinity. And then again, basically the same thing happens, for example, over here. And so you have another line over here, and so on and so forth. This line in mathematics is called the and there are 2 types of these. There is basically a vertical line like this, and there is a horizontal line that some functions have some horizontal, and there is a name for this. So you can, of course, now I have forgotten the name, but the point is that you can see this line over here. You can imagine that you have some kind of the same thing going on in here, and then you have basically these 2 straight lines, and having these 2 straight lines, you have basically, for example, let's say that this is your for example F2, and for example this over here becomes your F1, and then your hyperbola basically becomes something like this, meaning that it kind of tends towards that line. I basically take it like this, something like this, or something like this. So now if I have these lines over here, first it's going to help me draw my hyperbola basically more neatly, and moreover you can see that the hyperbola is kind of tending towards those lines. Of course, it's not going to be well, that's some thought for the future. You can play with this thought and see what sort of relationship there is between these lines and any basically possible hyperbola. You could take some specific cases and play with the thought if that interests you. That was just some thought that I got as I was working on these hyperbolas. Now there is one thing over here. So basically I have basically this point over here, I have this point over here, I have this point, and I have this point over here. I can call this point, for example, F1, I can call this point F2, for example. This is focus 1, this is focus 2, and this is a vertex of the hyperbola. I can call it A. This is another vertex of the hyperbola. I can call it B. And the coordinates of these points, we can define them over here. You see, basically the two vertices of a hyperbola are at a distance of 2a from one another, meaning that this distance over here is a. From the center to this point, this distance is a, and this distance is also a. That means that then this distance becomes 2a. So what that means is that the coordinates of this point would be basically a comma 0 and negative a comma 0. The coordinates of this point is going to be c comma 0, and this point would be negative c comma 0. That means that the distance between the foci of your hyperbola becomes basically 2c. Now basically there is one difference between, for example, a hyperbola and an ellipse, in that basically B is not, you don't really, I mean, necessarily you don't see it over here, or you do. So basically basically what I have over here is some line like this and some line like this, okay? And then I have, let me do the lines in orange so that we understand them better. And I have some line like this, and then I have basically this line like this and this line like this. Now there must be some relationship between the shape of your hyperbola and the slope of these two lines. That's something that we could, you can think about on your own if you would like to. But there is basically some distance over here which has been called some distance over here which is basically perpendicular to the x-axis, something like this. There is some distance over here that touches this line, and then if you from this point, if you draw perpendicular to the y-axis, this distance over here has been called b. This distance over here has been called b. This distance. Now there is some, of course we can play with this a little bit, see how that works out if we get the time. But then in the case of these hyperbolas, B has been defined as basically the square root of c squared minus a squared. I don't really know how they have defined this, but they have done so, and it basically fits with the rest of the things in hyperbola. So it's kind of like it's been introduced like basically like some kind of definition over here. Now for now you can just take it as a definition and use it in order to understand other things. But then there is also this clue over here that you can use in order to understand the relationship between different parts of this hyperbola if you would like to. So that is basically the hyperbola, and then you have 2c, 2ab, c, and a, and so on and so forth. So now what I'm going to do is that I'm going to just make a screenshot over here and then use this throughout our basically this demonstration. So where is that? So this is basically, I'm going to use this image over here. Okay, so that is that. Now what I'm going to, so now there are a few things over here that we need to talk about. First of all, we said that these are, as you know, as we mentioned before, these are the foci of the hyperbola. The midpoint, this midpoint over here, this midpoint of this line segment joining the foci, so the midpoint of the line segment joining the foci is called the center of the hyperbola. This is called the center. This is called the center. And the line through the foci is called the transverse axis. And the line through the center and perpendicular to the transverse axis is called the conjugate axis. So then this is called the transverse axis, and this axis is called the conjugate axis. So the point at which the hyperbola intersects the transverse axis are called the vertices of the hyperbola, which are these 2 points over here. And the distance between the two foci, as we said, is denoted by 2c. The distance between the two vertices is denoted by 2a, as you can see over here. It's pretty clear the way that I've written it. And here there is basically some indication to basically how the distance between the two vertices, or the length of the transverse axis, is basically, so the distance between the two vertices we denote that as 2a. So the distance between the two vertices we denote it as 2a, and that has been defined as the length of the transverse axis, meaning that the transverse axis actually starts from here, based on this definition, starts from here, goes all the way up to here. So this means that basically your transverse axis goes from here to here, and this is the length. This is the length of the transverse axis. Okay, that is basically based on the definition that I can see over here. And there is a quantity b that has been defined as the square root of c squared minus a squared. So this is more like a definition. I don't see any derivation or anything for that. It's just a definition that b is equal to the square root of c squared minus a squared. And so basically, if I assume that basically this length over here is b, then they have basically defined the length of the conjugate axis. They have defined the length of the conjugate axis as 2b, meaning that now if you imagine that for whatever reason this distance is b, if you imagine that for whatever reason this distance from here all the way up to here, this distance is b, you would get one same distance down here and down here and down here, and so from here all the way up to here you would have basically the length would be 2b, which is the length of the conjugate axis. conjugate axis. Now, of course, you don't need to worry about basically how to worry about basically you do not need to worry about calculating this thing because B is already over here, so you can find this distance based on this formula. That's how they have defined it. And that's basically the whole story here. Now let me there is one thing over here that we need to talk about, and that is the I wish I hadn't made so many changes to this image. Anyway, it doesn't really matter. We will do another one. So now, if you want to find the constant, now basically as we talked about these hyperbolas, we said that if this is your conjugate axis and this is your transverse axis, and if I imagine that, for example, I have this line over here, and I have this line over here, and I have this line over here, and this line over here, and suppose that I have these two distances over here, and suppose that this is my hyperbola. Suppose that this over here is my hyperbola. Okay. So this is basically my hyperbola, and suppose that these are your foci, F1 and F2. Now, if I pick any point over here, for example, P, if I pick this point over here, P, and connect it over here, P, X, comma, Y. Now, we said that this distance, basically, you will always have two foci over here. One of them is much farther away from P than the other foci, and the one which is farther away is F1 over here. So you can write PF1 minus PF2, and that was basically kind of like the definition of the hyperbola, that this distance is always a constant value. Is a constant value. So this constant value, we basically need to have some way to calculate that. Now, if I take these points as, for example, A and B, if I take these points as A and B, and of course you know that this distance, the coordinates of this point is basically A comma 0. I'm sorry, negative A comma 0. This is A comma 0. This is C comma 0, and this point over here is negative C comma 0. So PF1 minus PF2 in order to calculate this distance in terms of basically A, B, and C, or basically in terms of just A and B, and preferably in terms of A, what we can do is that basically you know that these 2 points, A and B, are also points on the hyperbola. So instead of the point P, you can simply take any of these 2 points, A or B, because you already know the coordinates of these 2 points. Now you take only this much. I take a few minutes rest, and I'll come back and we'll talk about the rest of this. Okay, so basically now if you want to calculate this distance over here, so instead of writing basically, so I've taken any point on this hyperbola, and then I've written PF1 minus PF2, meaning that the distance between P and the and the focus which is farther away from P than the other, basically, than the other focus, minus the distance of P with the focus which is closer to P. Now, since I don't really know the exact basically the exact coordinates of the point P, what I can do in order to calculate this distance over here, at least in terms of A or C, for example, is that I can take, for example, the point A over here. The point A, I already know that the coordinates of this point are basically negative A comma 0. And let me so now, by basically, if I take the point A over here instead of P, taking point A instead of P, we have basically this point over here, that the distance of this point from F2 is AF2, and minus basically AF1, and I can also take this point over here. Now taking for example point B instead, what we will have is basically BF1 minus BF2. So we have BF1 minus BF2. Now, since any point that I take on my hyperbola, on any of these two parts of the hyperbola, and if I take the difference of those 2 points, the distance of those 2 points, and so on and so forth in this manner, since this is going to be a constant, so therefore I can write basically AF2 minus AF1 is equal to BF1 minus BF2. And this color is a little bit weird, so I change it to some other color, like this. So then I have basically BF1 minus BF2 is equal to AF2 minus AF1. Now, instead of basically, as you can see, AF2 is basically AB plus BF2. AB plus BF2. So you can see that basically AF2 over here, AF2, this distance, you can break it down to AB plus BF2. AB plus BF2 minus AF1 is equal to BF1. So BF1, I can break it down to BA plus AF1. BA plus AF1. BA plus AF1 minus BF2. BF2 coming from here. Minus BF2. And, well, I can simplify these two, and I can take, for example, I can write negative AF1 minus AF1 is equal to negative BF2 minus I can actually keep this over there. What I can do is that let me do it this way. So I can write this as basically, so BF2 So I can write this as BF2 plus BF2. Take this to the other side of the equation is equal to AF1 plus AF1. And so what that means is that 2 times BF2 is equal to 2 times AF1. 2 and 2 you can cancel out, and that means that basically BF2 is equal to AF1. AF1. So BF2 is equal to BF2 is equal to AF1. This distance is equal to this distance over here. So that's something that we can use later. So now over here BF1 minus BF2 that we had over here, BF1 minus BF2 was equal to basically BA plus AF1 minus BF2 is equal to BA plus AF1 plus minus BF2 and of course, well, you know that BF2 is equal to AF1. So since this is AF1 negative BF2, you can cancel them out. These are equal quantities. One of them is positive, one of them negative. You can cancel them out. So that means that basically BF1 minus BF2, that distance that we were looking for, is equal to BA, which is equal to 2A, So basically then what that means is that any point that you pick on your, for example, this point P, if you pick on your hyperbola and basically subtract, for example, this distance from this distance, that distance is going to be equal to 2A. So that constant that we were talking about is actually equal to 2A. Now there is one more part over here about the eccentricity of an ellipse. There is one more part about the eccentricity of an ellipse, and there is not much information over here. So basically, as you remember, in the case of an ellipse, we said that the eccentricity, we calculated the eccentricity E is equal to C divided by A. Now also in the case of a hyperbola, the eccentricity has been defined as E and the same ratio C to A. And so if you have a hyperbola over here, as you know, basically, for example, let's say that this is your hyperbola, something like this, and this is your, basically these are your foci F1 and F2, then you know that this distance over here is A, and this distance is C. And the same thing over here, this distance is A and this distance is C. And you can see that basically C is basically greater than or equal to A, meaning that basically the vertex of your parabola, of course, can go all the way up to 0, or it can go all the way up to F2, and then of course your hyperbola gets a little bit basically wider. This part goes basically, moves to the top, this part moves to the bottom. But anyway, you can basically this vertex can move all the way up to here. So you can say that C is greater than or equal to A. And so since the eccentricity of the hyperbola has been defined as C to A, since C is always greater than or equal to A, then you can say that the eccentricity of a hyperbola is never less than 1. Is never less than 1 because C is always greater than A, less than 1. And of course, in terms of eccentricity, the distance of the foci from the center is basically, we said that basically is equal to C divided by A. That means that since the foci are at a distance of C from the center, so C here is equal to E times A. So then in terms of the eccentricity, the distance of the foci from the center is E times A. And that's basically all about eccentricity. So this is basically the situation here. Still, we have no problem here. We can still move on to the next things. And the next thing that we have over here is the standard equation of a hyperbola. And I suppose we will do that in the next video. We can break it down. We will do as much as we can in this video, and then we will move to the next video. Okay, so now about the standard equation of a hyperbola. About the standard equation of a hyperbola. So basically the equation of a hyperbola is going to be in the simplest form without having too much unnecessary basically details. If basically the center of the hyperbola is at the origin, meaning that when I draw a hyperbola like this, and this is for example the transverse, this is the transverse axis, and this is the conjugate axis. Then of course you know that the transverse axis is basically always the axis that goes through the foci. So that's the transverse axis, and the other axis which is perpendicular to that axis is called the conjugate axis. And this point over here is called basically the center of the hyperbola. Now, if this center is at the origin of our coordinate system, let's say that this is the coordinate system XY. If this center is at the origin O, for example, and the foci are along either the x-axis or the y-axis, meaning that the hyperbola is in this exact orientation, or basically or if you take this hyperbola, put it exactly over the center to center over here, and then you move it, rotate it basically 90 degrees counterclockwise, then this part would be somewhere over here, and this part would be somewhere over here. So in these two orientations, in the orientation that you just move the center over here and not rotate the hyperbola, the whole hyperbola, and if you basically rotated that 90 degrees counterclockwise, and then basically then your one part of the hyperbola would be up here, one part would be down here. In these two orientations, the equation of the hyperbola, of course, is going to be in the simplest form. And what we are going to do here is that we're going to basically calculate or derive the equation of a hyperbola that is in this orientation, meaning that if you have for example, your hyperbola somewhere like this, and then if the transverse axis, if this is the x-axis, and the transverse axis comes along the x-axis, and the conjugate axis comes along the y-axis, and then you would have, for example, some hyperbola like this. If I basically draw these two lines over here, something like this, and then the hyperbola would be something like this. Okay. Now, if you have this hyperbola over here, you have a vertex over here that has the coordinates. A, 0 and negative a, 0. And then you have this focus over here, which is, let's call it f1, negative c, 0, and c, 0. Call it f2, for example. And that's basically your hyper, and your hyperbola would of course be this thing over here. Would be this conic section over here. So if you do so, then basically the equation of your hyperbola is going to be equal to x squared by a squared minus, it's a negative sign, you need to pay attention to that, minus y squared by b squared is equal to 1. And so what we want to derive is basically now this equation over here. So now, of course, you know that before I start with the derivation, there are a few things that you need to know. For example, as some basically agreements that we can have between ourselves. We take this as the x-axis, we take this as the y-axis, we take f1, f2 as the foci, and these are the coordinates of the two foci. We take this point as these 2 points as the vertices of the parabola with these two, basically with these coordinates, and then of course you can imagine that for example P is any point on the parabola. This point P over here with coordinates x, y is any point on the parabola, and we already showed that basically PF1 minus PF2 was equal to 2a. And so if that is the case, then basically using some simple algebra we can basically show that the equation of this parabola is equal to this expression or this equation over here. So then you can basically calculate PF1 as basically P and F1 over here is negative C comma 0, and P is basically X comma Y. So if using the distance formula, you can write basically X2 minus X1, which is X plus C whole squared plus Y minus 0 whole squared, which is Y squared. And PF2, basically PF2 is equal to, basically using again this distance formula, is going to be X minus C whole squared plus Y squared. And of course, since that is the case, based on this equation, I can write the square root of X plus C whole squared plus Y squared minus PF2, which is basically this expression over here, X minus C whole squared plus Y squared is equal to 2A. Or I can write basically I can write the square root of X plus C whole squared plus Y squared is equal to 2A plus the square, taking this to the other side, plus X minus C whole squared plus Y squared. And then if I square both sides of this equation, what I will get is basically X plus C whole squared plus Y squared is equal to, basically this is A plus B whole squared. So A plus B whole squared is equal to A squared, which is 4A squared. 2 squared A squared is 4A squared, plus B squared, which is basically this whole thing whole squared, which is X minus C whole squared plus Y squared, plus 2 times A, which is 2A, times basically square root of X minus C whole squared plus Y squared, which is basically 4A times this expression. So that is plus 4A times basically X minus C whole squared plus Y squared, and that is that. Now of course you can simplify this a little bit, meaning that you can simplify Y squared with Y squared, and you can expand this part, X squared plus C squared plus 2 times XC is equal to 4 times A squared plus basically X squared plus C squared minus 2 times CX plus 4A times the square root of X minus C whole squared plus Y squared, which is equal to, and so then basically you can simplify X squared C squared, and then you can write basically 2XC, this one over here, minus 4A squared plus 2 times CX, this thing over here, is equal to 4A square root of X minus C whole squared plus Y squared, and that is equal to 4XC minus 4 times A squared is equal to 4A the square root of X minus C whole squared plus Y squared. And if I divide by 4, I get XC minus A squared is equal to a square root of x minus c whole squared plus y squared. And so if I divide by a now, I get x or c divided by a times x minus a is equal to the square root of x minus c whole squared plus y squared. And now if I again square both sides of this equation, I will get c squared by a squared times x squared plus a squared, and then I have negative 2 times c by a times x times a, and these two will cancel out. Negative 2 times cx, negative 2cx, negative 2cx is equal to basically x minus c whole squared plus y squared. So next what we have is I can expand this part, meaning that I can write c squared by a squared times x squared plus a squared minus 2 times cx is equal to x squared plus c squared minus 2 times cx plus y squared. And then you can cancel these two out. And then I can take this to the other side of the equation, write it as c squared by a squared times x squared minus x squared. So these two are taken care of. And then I have y squared over here, so minus y squared, this is taken care of, is equal to basically c squared minus a squared. So c squared is over here, a squared is over here. So everything is taken care of here. And so I can add these two together. So I can write x squared times c squared by a squared minus 1 minus y squared is equal to c squared minus a squared. Now this thing over here is equal to basically x squared times c squared minus a squared over a squared minus y squared is equal to c squared minus a squared. Now I think in the previous video it was that we said that we defined some b, which is not here anymore. We defined b as the square root of c squared minus a squared. C squared minus a squared. So that means that basically c squared minus a squared is equal to b squared, or b squared is equal to c squared minus a squared. So instead of c squared minus a squared, I can write b squared. So that would be b squared by a squared times x squared minus y squared is equal to b squared, again c squared minus a squared. And now if I multiply basically by a squared, I will get b squared times x squared minus a squared y squared is equal to a squared b squared. And if I divide by a squared b squared, I'll get b squared x squared divided by a squared b squared minus a squared y squared divided by a squared b squared is equal to a squared b squared over a squared b squared. So this is 1. And over here you can cancel these two out. Over here you can cancel these two out. So you'll get x squared by a squared minus y squared by b squared is equal to 1. And that is basically the equation of the hyperbola we were looking for. So then you can say that any point, so you can say hence any point, hence any point on the hyperbola satisfies the equation. This satisfies this equation. Satisfies, let's say, equation, for example, number 1. Equation 1. Now, what we have shown, so basically, what we have shown so far is that if any point is on the hyperbola, it's going to satisfy this equation. Now, one more thing we need to show, so that basically this, so that our proof is complete, or basically so that we can use this formula in two different ways. Meaning that right now I can what I can do is that I can basically find any point. I can basically take my hyperbola, for example, in this orientation, and take this point over here, read the coordinates of this point from the graph, and then if I have the coordinates of this point, for example, P as x1, y1, then of course I know that x1, y1 is going to satisfy this equation. But I still cannot use this equation in the other way around, meaning that, for example, if I have some random point, for example, Q as x2, for example, y2, I should basically be able to use this formula, meaning that I should be able to substitute this point in this formula in order to check whether this point is actually on the parabola or not. But still I don't know whether this formula would be good enough to do that for me or not. So what I want to do now is that I want to know if any point satisfies this equation, is that point going to be on the parabola or not? So far we have shown that any point that is on the parabola is going to satisfy the equation. But now what I want to prove is that if any point satisfies this equation, is that point going to be on the parabola or not? Meaning that I want to basically know if the formula does that for me as well. So the next part, and that part we are going to do in the next video, because it's going to take some it's easy, of course, simple, but it takes some algebra to show that basically that is also the case, and then we will get to the rest of the things. So I'll end this video here and we will continue in the next video. See you in the next video. Thank you.